is I am going to teach you today is the velocity potential function, the stream function, and rotational components in x, y, and z direction. Okay, the velocity potential function is one, stream function that is second one, the third one is rotational components. Okay, dear students, these are the new topics which you have not studied in the previous course. Okay, so one by one we will study in detail here, and it is important. Many numericals are based on these three only. Numericals are a little bit tough, as I told you. Convective, local acceleration, stream function numericals are little bit difficult. Okay, no issues. The first function what we'll discuss now, velocity potential function. The velocity potential function will be represented by a symbol that is phi, and is defined as, okay, please read the sentence carefully, is defined as a scalar function of space. So it is a function of space. So what does it mean? So phi is a function of space. Dear students, space may be x direction, or it may be y, or it may be z. So I will write all three. It is not only that it is only pure depends on x, pure depends on y, not like that. It is a function of space. So I have written all three. It may be only depends on x, depends on y, or maybe depends only on z, or depends on any other space coordinates, and as well as time t. So it is depends on time t, such that its negative partial derivative means the negative partial derivative of this phi function is equal to, with respect to any direction, negative partial derivative of phi with respect to any direction gives the velocity in that direction. So if you read these two lines, it will be very difficult to understand. So what I do, I will write on mathematical equation, so it will become easy for the understanding. So mathematically, velocity potential function, as I told, is a function of x, y, z, and as well as it is function of time. It is clearly it is given function of time also. Now come to this point. This is in such that it's negative partial derivative. So what I do, I will take a partial derivative of phi, negative, negative, negative partial derivation of stream function with respect to any direction. With respect to any direction, you write direction. It may be x direction, it may be y direction, or it may be z direction. Gives the velocity or equals to, or it gives the velocity in that direction. Velocity in that direction, in particular direction. I will write here, in that particular direction. In general. Now, dear students, can you apply for mathematical equation? So minus the negative derivative of stream potential function with respect to any direction. I will take, for example, x direction is equal to velocity in that particular direction. So velocity in x direction is what? That is u. So this is a velocity potential function. Okay, so please read once again. If you maybe you have some little bit doubts in your mind, let me take a different color chalk piece and explain once again. Okay. Now look at once again. We'll read velocity potential function will be represented by a symbol that is phi. Okay, it will be represented by symbol phi, and it is defined as a scalar function. It is a scalar function only, depends on space and time, and in such that its negative partial derivative, negative partial derivative of this phi function with respect to any direction, with respect to any one direction you take, any one direction, which gives the velocity, in that direction, means in which direction you have differentiated, in that particular direction you will get the velocity. So now, dear students, can you apply for the y direction? So how it will be? So the negative derivative of the stream velocity potential function with respect to y direction, it will give the velocity in y direction. Velocity in y direction will be represented by v. So this is one velocity potential function in y direction. Similarly, can I write like this? Negative derivative of stream velocity potential function with respect to the z direction will give the velocity in z direction. The velocity in z direction will be w. So this is one velocity potential function. Now the continuity equation in three dimensions. What is a continuity equation in three dimensional? Continuity equation in three dimension. So what is continuity equation? Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is a continuity equation and it is for incompressible. It is for incompressible fluid. Incompressible means density is equal to constant. Density equal to constant, not 0. It has some value. That is, I have not taken rho in these three terms. And as well as it is for steady flow because there is no velocity term with respect to time. Dou u by dou t illa. So here this is a continuity equation. Now you substitute the value of velocity u, substitute the equation of v, substitute the value of w from the above equation. Here it is there. Using these three equations, you substitute the values. Now one by one I will substitute. Okay. First what I do, I will take dou by dou x. What is u? U is minus dou phi by dou x. Substitute minus dou phi by dou x plus dou by dou y as it is. What is v? V term is here. Minus dou phi by dou y plus dou by dou z. What is w? W term is here. So minus dou phi by dou z and it is equal to 0. Now you multiply these two differentiation terms. So what you will get? Minus dou 2 square by dou x square minus dou square phi divided by dou y square minus dou square phi divided by dou z square is equal to 0. Dear students, you take minus common in all the terms. So dou square by dou x square, if you take minus common, this term will come plus dou phi dou y square, dou square phi upon dou z square is equal to 0. So if you send this minus sign on the right hand side, the equation will be dou square phi upon dou x square plus dou square phi upon dou y square. If you write only these two, it will become for two-dimensional flow. If you write all three, then it will be for three-dimensional flow. But for your course, it is only two-dimensional flow. There is no much numericals on three-dimensional because it is a basics fluid mechanics course. So if you are going for advanced fluid mechanics course like MTech or any PG courses, then it will be for three-dimensional flow numericals. So here this is the equation of stream function, or it is also called as Laplace equation. You have studied in mathematics, Laplace equation. So what is the use of this Laplace equation here is, he will give the value of some function phi. Some function will be there, it depends on x, y and z. You calculate dou square phi upon dou x square and as well as dou square phi upon dou y square. And if that equation gives equal to 0, then this meaning is it is a case of fluid flow. Case of fluid flow. So what do you mean by this? What does it mean by case of fluid? Means the fluid is flowing from one point to another point. If this equation is not equal to 0, if you got any one function after calculating all these, if the equation is not equal to 0, means the fluid is not flowing. It is maybe at rest. That is what meaning of these Laplace equations here. Understood? It is there, some numericals are there. We will anyways will solve later. Understood? He will be given some function phi. Some equation will be given like phi is equal to 2x square plus 4x, like this. Some equations will be given. Using this velocity potential function equation, calculate the Laplace equation. If you equal to 0, if you got 0, then there is a case of fluid flow. Means the fluid is flowing from one point to another point in a pipe. If you not got equal to 0, if it is not equal to 0, then the fluid is not in motion. It is maybe at rest.